Hello everyone, my name is Pratyush. I am an AI resident at Apziva, and this video is going to be a quick rundown of my project, which is titled as Voice Cloning and Fake Audio Detection. And throughout this video, I'll be going over the phases involved in the project, what strategies I adopted during each phase, my rationale behind adopting those strategies, and in the end, I'll give you a quick demonstration of my end-to-end final product. So let's get started. Before I proceed further, let me just give you a brief context about the project itself. So, the client for whom I was building this project, they were based in the cybersecurity space, and their end goal was to build a product, a tool basically, that detects whether an audio sample is fake or real. In simpler words, it's a classifier. So it's supposed to correctly classify whether a given audio sample is fake or real. A real audio sample would be any audio or sound bite that hasn't gone any sort of tampering or synthesization. Could also be a real person speaking. So a snippet of a real person's voice. And a fake sample would be the cloned version of a real sample that has indeed undergone any sort of synthesization, like tampering with its amplitude, frequency modulation, or beat anything else. So that is how we define a real and a fake audio sample. And this project was not just about building that fake audio detection mechanism, but also implementing our native voice cloning mechanism as well. So we don't just have a fake detector, but also a VCS, which is an abbreviation for a voice cloning system. So in this project, what I do is first I fetch real time audio samples, use a transformer to create their clones, and based on that new data set, then I build my training and testing model. So it has two levels. First, building the VCS, and once we have the VCS implemented, we have our fake or the clones of real audio samples generated. Based on that data set, then we build our fake detection model. So it has two levels. And since it's a classifier, our key success metric to gauge the performance of the classifier, there were obviously traditional classification metrics like precision, recall, accuracy, with a special emphasis on the F1 score. The reason being because it acts as a balancer between precision and recall and gives a clearer picture of how the model is actually performing. So F1 was the main measure, but I also reported the other classification metrics as well. This one was for the fake audio detector, whereas for the VCS, my main metric was WER, which is the word error rate. Basically, what this word error rate measures is the rate or the percentage of words matching between a real audio sample and its clone. Lesser the word error rate, the better it is, as in it you can infer that our cloning mechanism, our VCS, has effectively cloned maximum number of the words from the real sample. So our end goal is to minimize the word error rate and have a healthy maximum F1 measure. Now coming on to the data set, for this project I was provided two data sets. One data set was called TIMIT, and this was my main training and testing data set. It had around 630 speakers and 10 real audio samples per speaker, out of which 4,620 audio samples were provided for training and the remaining 1,600 for testing. And I load this data set using a library called Deep Lake. It provides you timid samples only a read at a read-only access level. So what I do is first I read those samples, store it in an appropriate data structure, and then continue with the further processing. So this is my training and testing data set. And then there is a second data set which is called CommonVoice. And CommonVoice acted as my data set for the ground truth. So CommonVoice basically has audio samples from real people speaking. So that is my ground truth data set. As in, I tell my model, see, this is what a real audio sample looks like, or should ideally look like. And based on this, now you have to identify whether any incoming audio byte or any sound byte or a WAV or MP3 sample, whether this is fake or real, detect it accordingly. So that's the purpose of this ground truth dataset. Now, this was my first phase, which was the voice cloning system. Let me just show you what what were the steps involved in them. I hope you can see it now. Yeah. So first, I simply load the TIMIT dataset, perform some unit testing on a random sample. Then I extract the metadata like speaker ID, transcripts, timestamps, etc. And finally, I convert the tokens from the transcripts into embedding vectors, which will like later on go into my classifier as the feature set. Once I have all these artifacts ready, then I implement my VCS using a transformer called SpeechTT5. So this is a sound transformer model provided by Microsoft, and I use this library to create audio clones of around 5 to 6 real samples per speaker. And once I have that, I efficiently organize my data set into a proper directory structure. So finally, what my data set or my directory structure would look like is I'll have a training set, I'll have a test set. Inside a training set, I'll have fake audio samples and real audio samples, about 2,300, oh sorry, not 2,000, yeah, 2,300 real samples and their corresponding clones, and about 840 fake samples in the test set and their corresponding clones. The reason behind putting them in a standard directory structure is that when we later on pass these audio samples as dataset into the classifier, we do not encounter any bottlenecks related to like any standard directory structure, or prevent any sort of mismatch, organizational mismatch. So it's a good practice to have our data files or our sound clips in a proper directory structure for the training and testing mechanism later on. But before training and testing, there was another phase involved, which was signal processing and consolidating my data set. In this, what I simply do is I consolidate the timid samples with the CommonVoice ground truth, ensure that all of their formats are consistent. They all should be in WAV format, and I ensure that. And once I have that, I don't just consolidate the files, I also consolidate their metadata and ensure that each sound ID or each audio ID is correctly labeled. As in, if it's coming from the ground truth dataset, it should be labeled as zero. Zero as in it's not fake. And if it's a cloned TIMIT sample, then it should be correctly labeled as one, which means it is fake. Once I have that, then what I do is I check some inner details, or like how a real audio sample differs from a fake sample at a more granular level before actually building the model. So let me share with you the observations. So as you can see, yeah, here it is. So we have the waveform and the spectrogram, amplitude and frequency distribution of of a random real audio sample from TIMIT and its corresponding clone. You can see that although both of them are the same, I mean, same as in they have the same word structure or the wording composition, but their frequencies and amplitudes differ significantly. And you could see that in the fake sample or the clone, it seems like there is a deliberate attempt to make it more uniform. So it gives the model a certain hint that, yeah, this soundbite has been tampered with, may be fake. And same thing it is in the spectrogram as well. You can see more ridges in the fake sample and more darker sections, which means background erasure. So it tells you that some sort of backend mechanism has worked on this fake sample to kind of, erase the background, make it more uniform. Basically, this is what the VCS is doing, the SpeechTT5 Transformer. So that is how the model is supposed to analyze the patterns in these sound bites. And let me now go down further. This is simply the waveform and the spectrogram of a common voice sample, the ground truth sample, and you can see that it is fairly irregular or devoid of what we call it naturalness. A real sample should not look suspiciously natural or untampered with as compared to a sound bite or a clone generated by the VCS. So you can see those imperfections captured in the common voice sample as well. More number of ridges, less background erasure, non-uniform amplitude pattern, and all of those. Like it's very similar to this one, the real sample from the TIMIT dataset. So once I have these ideas, these patterns analyzed, these patterns captured and captured as feature set for the classification model, then I go to the third phase, which is actually building that fake audio detection mechanism. And to build that classifier, I implement a convoluted neural network, a CNN, in which I pass the consolidated data set, TIMIT, along with the common voice ground truth. And then there's the standard procedure. Split the data set into training, testing, and validation. For this, I have 70% as my training set, 15% as the validation, and the remaining 15% is the unseen test set. Once I have that, I define a blueprint for the neural network. So since this does not have a need to build a 3D neural network, I built a standard convoluted to a 2D neural network for this. Use the standard rectified linear unit as the activation function, and then expose my output layer where we pass the target column of the label, which is either 0 or 1. 0 for real, or you can call it non-fake, and 1 for the fake audio. Once I train that model for the optimal number of epochs, I have the results, I have the model built, then I evaluate its performance, the same classification metrics and the word error rate. And just to clarify, the CNN model has been built using PyTorch. So after my training, I save this CNN model as a PyTorch file, which later on goes in as an input in my end-to-end solution as well. So once I have this model built, I generate the classification report. As you can see, we have the confusion matrix for the training set, validation set, and the test set. And you could say, suspiciously or surprisingly, I get a perfect F1 measure of 100% on the test set. And I kept on revisiting again and again, trying to confirm whether the CNN is overfitting or not. I keep on tuning the hyperparameters, keep running it over and over again, and every time I get a perfect F1 measure. Sounds too good to be true, but it also attributes to a limitation in the dataset as well. The reason being, I have a very small sample space of only two data sources, effectively only one. In fact, my training and testing has been done using only one dataset, TIMIT, and CommonVoice is my ground truth. So I do not have a more diversified dataset of fake samples because I'm generating the clones via my custom or native VCS. So in a way, this model would only detect a fake from a real if any kind of similar transformation or a cloning mechanism has been applied. In other words, if a clone or a synthetic audio sample has been created using SpeechTT5 or any other similar model. So that's one limitation of it, but otherwise the blueprint is pretty standard. And we can see that in fact, on the test set, the neural network performs better than the training set as well. So in the training set, two real samples were detected as fake, whereas in the test set, none of them. Everything has been correctly labeled and classified. And even in the training set, none of the fake samples have been detected as real, because that's what our main concern about the model was. If a real sample is classified as fake, not a very bad precedent, but it can be avoidable, or it can be manageable at the production level. But if a fake sample gets identified as real, then it bring opens up a can of production level issues. So thankfully, this thing is as minimized as possible. So these were my classification metrics. And coming to the word error rate, so I have an average word error rate of 48%, which means 52% of the words in a real audio sample on an average match with the words in its clone. Decent, not very good or like outstanding. Ideally, like had it been under 30%, it would have been perfect. But yeah, so since this is an average, if it's an average figure, it's decent, or I would say like, fairly manageable. And this is the distribution of the word error rate. And as you can see, this is a near normal distribution, slightly right skewed. Had this been a little more central, we would have had a perfect normal distribution. But still, missed slightly on this part, but it's not a make or break issue. So yeah, it's decent. Plus, augmented by the pitch perfect F1 measure. And once I have all these success metrics recorded, I finally deploy the neural network classifier at real time using a fast API app service. So I'll be showing you the demo shortly, but this is what my full real-time deployment architecture looks like at a full stack level. The user uploads an audio byte to the fast API web service, which is running on an Nginx server, and on another API endpoint, the web service calls the PyTorch model, the PyTorch file of the neural network model. It runs on the input soundbite and generates a list of outputs. So the first result is obviously the fake or real detection results. It generates the waveform and the spectrogram visualizations. And third is by far my favorite and the most fun output, that is an AI generated summarization using GPT-o3 Mini. So what I do is I consolidate the waveform and the spectrogram into a pandas data frame, convert it into a string, and pass it in the ChatGPT API model, the GPT-o3 Mini model, as its context. And based on the waveform and the spectrogram, the generated visuals, the GPT-o3 Mini generates a quick summary of it. And that is how my entire deployment structure works. And this fast API web service, it runs on an Nginx server that is triggered by a batch script. So before I show you, sorry, this image does not open. So this is how the Nginx server runs. I simply open up the batch file, and and once the batch script is running, I have my fast API also runs on it. Now let me show you the main application. This is my home page. Now before I like perform real-time detection, let me just quickly show you a real sample and a cloned sample for reference. Let me just open them up real quick. So for testing, what I've done is I have recorded my own audio sample and created a clone of it using SpeechTT5. First, let's hear my own voice. Hello, this is recording one, two, three. I hope you heard this. Let me play it once again. Hello, this is recording one, two, three. Okay, this one was the real sample. Now let me play the clone.
Hello, this is recording 123.
I'll play it again.
Hello, this is recording 123.
Okay. Now let's perform live real-time detection. First, I'll upload the real sample, my own voice. Now this runs. Perfect. Yeah. So you can see it predicts it as real with a confidence of 17%. Pretty decent. Like at least it's getting the real audio sample correctly. And here we have the AI generated smart explanation that explains why the model predicted this as real based on the waveform and spectrogram. This one was the real, but the main test remains, which is detecting a fake audio sample. That's what we'll call it, the trial by fire of the fake audio detector. So let's now upload the clone sample. I'll click on analyze. Let's wait for a while. Let's wait for a while. Perfect. Now, as you can see, this sample has been detected as fake, and not just detected as fake, but detected as fake with a confidence of approximately 82%. So in detecting a fake sample, our model passes this trial by fire with flying colors. And as you can see, the AI generated smart explanation, which is generated using GPT-o3 mini, its waveform, and its spectrogram. So this is what my final end-to-end solution is. And this brings us to the end of my demonstration, my full demo. I hope you liked this video. Thank you for listening to me. And I'll be posting the link to my GitHub report in the video description. Please go over that. If you have any questions, comments, or concerns, please do feel free to reach out to me. I'll be more than happy to engage with you. And thank you so much for listening once again. Signing off.